Hi, so we're in section 3.3. Section 3.3 is entitled Chebyshev's Rule and the Empirical Rule. So in this class, we're only going to be doing the empirical rule, and I'll put it up on the board. Okay, so the empirical rule explains how a distribution is spread out if the distribution is bell-shaped. So you have to start with that. So if a distribution is bell-shaped, okay, then we're going to make some statements about how many observations are within one standard deviation of the mean. So we look at the center of a bell-shaped distribution and we have the mean, okay? And according to this rule, the empirical rule, if we go over it to the left by one standard deviation and we go over to the right by one standard deviation, we're going to capture 68% of the data, right? So let me draw this here. Coming up, maybe the dashed lines are helpful. Okay, that is going to be 68% of my observations. I'm just going to go through the empirical rule once in this general form, and then I'm going to go through the example in the notes so that maybe it'll make more sense too. So kind of saying it twice. So if I move over 2 standard deviations, mean minus 2 standard deviations to the mean plus 2 standard deviations, then we have 95% of the observations. So because the shape of this distribution is bell, we got this big bell in the center capturing 68, and then as we come down, we capture some more, 95 between these two goalposts here. And then finally, the third part of the empirical rule says that if we go over 3 standard deviations in each direction, then we're going to capture almost all of the observations, 99.7. So if we come up here and we come up here, then in here we have 99.7% of the observations. Okay, what does all that mean? Let's take the example in the notes, and I'll draw that picture up here for us so we can kind of get a more concrete example. All right, suppose the number of cars that pass a given intersection in a day is known to be roughly bell-shaped with a mean of 375 and a standard deviation of 25. So let me go ahead and draw that roughly bell-shaped distribution. Okay. And we are going to write here, up here, that X, we'll let X stand for the number of cars that pass an intersection in a day. And we know that it has a mean mu equal to 375 and a standard deviation sigma, population standard deviation sigma, equal to 25. Now, you see how I lay out my bell curve here? And this is how we will always lay out bell curves. We'll put a variable name at the top, and next to the name, we're going to give it its 2 parameters, mu and sigma, so that when you look at the picture of this distribution, it becomes obvious what's going on, where the center is, and how spread out everything is. So what I want to do is I want to find the mean here. I'm going to draw a picture of the mean, right? And so that mu is equal to, a little bigger, mu is equal to 375. And the empirical rule says if I go over 25 in each direction, 1 standard deviation in each direction, then I'm going to capture 68% of the data. So let's go ahead and we take it down here. So that's 375 plus 25, and so that's equal to 400. That's that point right there, and this point here is going to be 375 minus 25. So this point here is 350. So we're seeing that the one standard deviation interval runs from 350 to 400. And what the empirical rule tells us is if the distribution is bell-shaped, which we were given in the statement of the problem, that our variable number of cars passing an intersection has the bell-shaped distribution. So then we know that within the one standard deviation interval, right, 68%. That looks very messy. We won't do that. Okay, let's do this. So I'm going to shade the one standard deviation interval. And we have 68% of our observations are in that one standard deviation interval. So two pieces of information we just put up on the board. I showed you what the one standard deviation interval is, 350 to 400. And then with shading and indicating in the arrow that 68% of the observations are in that one standard deviation interval. Okay, I'm gonna give you, I'll draw the two standard deviation interval over here. All right. And we know that this is the same distribution. We have mu as 375 and sigma's 25. And then down here, this is my my mean is equal to 375, and I'm going to move over 2 sigma. So 375 plus 2 times 25. Okay, so that's 375 plus 50. And that gives me 425. 425 is going to be the upper end of the 2 standard deviation interval. So we're going to come over here, and we're going to get 375 minus 2 times 25 for the lower bound of the 2 standard deviation interval. 2 times 25 is 50. We're going to subtract that from 375, and we get 325. So we'll draw a picture of what the 2 standard deviation interval, the shading here, all of these observations are within 2 standard deviations. And the empirical rule says that the 2 standard deviation interval has 95% of the observations. Okay. All right. And additionally, what we know because of the empirical rule is that what's left, what's not either within your 1 or your 2 standard deviation interval, is that we have symmetry. So over here we have 68% in the middle, right? And then how much is in each tail? So what percentage of cars, what percentage of days do we have less than 350? What percentage of days do we have greater than 400? So here's a calculation which becomes very important in the class. So take some time and let's get the attention up, right? So we know that there's 100% of the data underneath this bell-shaped curve. That's what the distribution is illustrating. And in this tail, we're going to take 100% and we're going to subtract out the 68%. And then that's how much we'll have in 2 tails. So we have 100% minus 68%. And then that's what's in the 2 tails. And by the fact that the 2 tails are the same size, we're going to divide it by 2. So we end up with 32% divided by 2, or 16% in the lower tail, and we get 16% in the upper tail. The tails have the same amount of observations in them, that it is a symmetric distribution. Okay, all right. And so take a minute and figure out what percentage of observations are greater than 425, okay? Same kind of argument, let's go ahead and do that. So it's gonna be similar to what we had just done. The two tails have 100% minus 95%, and then each tail has 100% minus 95% divided by 2. So the two tails have 5% together, but each tail has 2.5%. Okay, that's coming on a quiz. So make sure you can do that. Let's see if I think we have another question on the notes to help us with that. Okay, so the example, I'll erase the board, read in the notes as I get the board ready. The average age of retirement, that's the problem we're going to be working on. Okay, so the average age of retirement for an entire population in a country is 64 years, and the distribution is bell-shaped with a standard deviation of 3.5 years. Okay, so let's go ahead and draw a picture of that. X is going to be the age of retirement. This distribution has a mean of 64 and a standard deviation of 3.5. Okay. We are asked, what is the approximate age range in which 95% of people retire? By the empirical rule, we know that that's the 2 standard deviation interval. So we're going to look for the 2 standard deviation interval, right? And so that's going to be 64 minus 2 times 3.5. That is mu minus 2 sigma. This is going to be an interval to 64 plus 2 times 3.5. Okay, so it's 64 minus 7 to 64 plus 7. And 64 minus 7 should be 57. And this 64 plus 7 is 71. And so I'm checking. What we know is that 95% of the people in this country retire between 57 years old and 71 years old. So let's go ahead and draw that on the graph here. So we have the center here is at 64. We're going to move over 7 to get to 57, and we're going to move down 7 to get to 57. We're going to move up 7 to get to 71. And what we know by the second part of the empirical rule is that 95% of our data is between 57 years old and 71 years old. Okay, so in terms of questions for quizzes, here we go. All right, this is one of my favorite ways of asking this question. We would like to know what percentage of the population retire at 57 years or older. So we are looking for the percentage of people that are 57 or older, greater, over to the right. So we are looking for an estimate of this whole centerpiece plus color here. I want to add to it that tail as well. Okay, so it's not just 57 to 71, but we also have to add the 71 up to the high end of the distribution. So, okay. How are we going to calculate that little red tail? You're going to use the same method that we had just used before, right? So we're going to find the area in both tails and then divide by 2. I'll just go ahead and do this part in red here for the tail piece, and then we'll add them together. So the two tails have 100% minus 95%. All right, and one tail has half of that. So it's 100% minus 95% divided by 2. 5% divided by 2, or 2.5%. Okay, so we know that the number of people that retire at age greater than 71 is 2.5%. So the total number of people that retire at an age greater than 57 is going to be the 95 plus the 2.5. So we have 95% plus 2.5%, and that gives me 97.5%. So that's the answer to the second question in the notes. What percentage of the population retire at 57 years or older? All right. See you next time.